Hello students, continuing our lectures on solid state physics. We will take up diffraction in this lecture. So diffraction is when an incident beam of light having this is the wave to the power I k dot r is incident on the specimen. It gets diffracted, and refracted wave number is k dash. So we have to the power I k dot r as incident beam, and outgoing beam is characterized by to the power I k dash dot r dash. So this is how this change in this wave number k dash k to k dash takes place, and the difference between the two. This is actually called the scattering vector. Now, so we have a difference in the phase factor k minus k dash, and we have a local electron concentration. So we get the scattering amplitude as equal to integration of local electron concentration, the exponential of this difference in phase factor, as delta k, as we have said, is a scattering factor. Now this value of f, scattering function, it is equal to fng. That means this value v into volume into the concentration. If this scattering vector is matching with the reciprocal lattice, and if it is not matching with the reciprocal lattice, then the scattering amplitude goes to 0. Now these magnitudes of the two wave vectors after and before diffraction is same, and to have this condition, that means this is actually the diffraction condition, and if you put it into the equation, this is what we get: 2k dot g is equal to g squared. This is actually the condition of diffraction that has to be satisfied. Again, by Laue condition, this is the Laue condition that the scattering vector should be equal to the reciprocal lattice vector, and so we can have 2 pi. If we take the dot product of these two, we can have v1, v2 and v3, which are the coefficients of the reciprocal lattice vectors. And we can also have something called de Waal sphere construction, which are the reciprocal lattice points, and diffraction will only take place when the de Waal sphere consists of both the incident and diffracted lattice points. Next we have the Brillouin zone formation, k dot half g is equal to, this is the Brillouin zone formation. So we have a reciprocal lattice. So firstly what we do here, so this is actually the first Brillouin zone. This is the first Brillouin zone. We have the perpendicular bisectors. From this point we draw the nearest points. We draw the nearest points, and we just draw the perpendicular bisectors, and the area covered by the perpendicular bisectors, it forms the first Brillouin zone. So this is Brillouin zone number 1. This is the first Brillouin zone. The next nearest perpendicular bisectors are these points. So if you again cut it, so this will make the second Brillouin zones. These areas make the second Brillouin zones. Yellow one, and again these are the last perpendicular bisectors, so we again draw these. So these areas, this one, and this one, they will form the third Brillouin zone. So basically formation of perpendicular bisectors.